Yes, thank you very much for the introduction. And I should say that there was a plan to have Steve Selvidge give this mini course a long time ago. So he was approached by the other three organizers to do that, and he agreed. And of course, that he passed away, I decided to take over because I know roughly what he was going to talk about. Of course, nobody can replace Steve. I'm not trying to do that. But I dedicate this mini course to his memory. I share a lot of folders with him, unfortunately, all unfinished business. So this is what I'm presenting is not somehow one result, but it's a kind of philosophy how one can tackle problems on stationary spacetimes using spectral theory, and maybe that's also related to what we've seen before. And so some of it is finished, and some of it I'm still writing up. But I'll try to give you a very elementary overview of what this looks like. And so let me just explain to you what a spacetime is and what a stationary spacetime is to fix the notations. Okay, so we start with an n-dimensional spacetime, and G. So G is the metric, and by spacetime I mean a time-oriented Lorentzian manifold. And I choose the wrong signature convention, which is, so the signature convention is minus, plus, plus, plus. And this means that locally, we can bring this metric to the following form. So locally, metrics we will be able to fix it like this. So n squared, which is a function, a smooth function on the manifold, or in the neighborhood where I'm fixing this. So dt would be some kind of time-like coordinate and plus some Riemannian part and spatial coordinates, some Riemannian type metric h here. So I'm not going to specify this too much more. So we have n is a smooth function on M, positive, and h, ij, some tensor, symmetric tensor. I'm assuming that this, well, metric 2 tensor, and I'm assuming this is positive. So these are the spatial coordinates. This is the time coordinate, and the convention will be dx0 will be dt throughout. So this, because of this wrong signature convention, one has to say more stuff. So the other convention is that I'm considering d by dt future pointing, and dt also future pointing. The forward geodesic flow goes backward in time. Slightly annoying, but one can live with this. And so this Lorentzian structure then at every point gives us a light cone. So what does the tangent bundle look like? Or maybe for our purposes more appropriate the cotangent bundle, but maybe let's use the metric and fix some isomorphism between those two. So at every point the cotangent bundle looks like this. So we have a future light cone and a past light cone. And so what's the inside? I will call V plus, backward light cone V minus. And then I have the null directions, so N plus and N minus. And I have the closure of the forward light cone, which is the open forward, the inside, and the null directions together. And the same for the past one. This is the convention. So I would say that these are called the causal, so future and past pointing causal vectors, or covectors. And then there is this notion of global hyperbolicity. So what we really want to do is we want to solve the wave equation. And it's known that the wave equation, the linear equation at this moment, the wave equation can be very well solved on globally hyperbolic spacetimes. So there is this notion of global hyperbolicity. There are more and less frightening definitions. I'll try to give you the least fright, and this to me least frightening one is that there exists a Cauchy surface. So this means, by definition, this means there exists a Cauchy surface. Well, I wanted to say space-like, and I'll say it now here in brackets. So space-like Cauchy hypersurface of codimension 1, smooth, And what's a Cauchy hypersurface? That's a surface that is intersected by every causal curve, maximal causal curve, exactly once. So what's that here? So sigma intersects any maximal causal curve exactly once. Okay, what's a causal curve? That's a curve whose tangent vector is causal at every point. So these are basically, as an observer, you can travel on those. If you're a light-like curve, then of course you're traveling at the speed of light, but it means that you're not going faster than the speed of light. And so what this means here, what goes wrong if you're not globally hyperbolic is if you're missing points. So that's some kind of completeness. Or what could also go wrong is that you have closed time-like loops. In this case, you would intersect the Cauchy surface more than once. Okay, so exactly once is once, no, greater 0 and smaller than 2. Okay, let's see what's on the next page. Oh yeah, so there are other definitions, but there is a very serious consequence. So there is a theorem, an old theorem by Geroch, that states that this has a very serious consequence, namely that it's topologically this will be a cylinder. But there is a newer theorem which sharpens that a little bit more, which says that smoothly this is a cylinder. So that took a while. So this is Bernal Sanchez, I think actually after 2000, which says the following. So M is actually equal to R cross sigma, and that the metric can be brought to this form here globally. So this is the t variables, this is the x variables, minus n squared dt squared plus ht. So ht is a smooth family of metrics of Riemannian metrics on sigma, and n is the function on m. So n here is a smooth function on m. So it still depends on time. And ht is a smooth family of metrics, really, of Riemannian metrics on sigma. So there is nothing going, no topology change going on if you have a globally hyperbolic spacetime. Okay, so that's simple enough. So what this tells you here, and this will be important later, you can get rid of the off-diagonal terms here by doing coordinate transformations. In fact, you can actually even get rid of that. But maybe there is a price to pay because n then depends on t, and maybe sometimes you don't want that. So if you, for example, think of Schwarzschild and Kerr, so Kerr, you would still have off-diagonal terms in there because maybe sometimes you want your metric not depend on the time coordinate. Okay, let's talk about wave equations. So what do I mean by this? And of course, as a pure mathematician, I want to be as general as possible, but without talking about Lipschitz. So I'm still going to be in the smooth category. So that's not very general, but that's just how, how pure mathematics seems to work. So I want to be as general as possible in the sense that I want to allow myself systems. That's why I want to introduce a vector bundle. So, which, if you don't like that, you can always take the trivial vector bundle. So that's going to be a complex vector bundle. And I'm going to endow it with a Hermitian structure, so an inner product. Well, I have vector bundle twice. That's all I need, I think. And then I'm going to fix an operator P. I think later I call it square. Let's see if maybe I want to change that. No, it's okay. So an operator P. So this is going to map smooth functions taking with, the operator takes vectors to vectors. It acts on the sections of this vector bundle. And I want this to be a differential operator of order 2. Order 2. And called normally hyperbolic, it's just a notation. Normally hyperbolic. I think a nice notation would also be of D'Alembert type, if it looks like the D'Alembert operator, but on the principal symbol level only. So normally hyperbolic, so that I define here. So if P is in local coordinates of the form minus Gij, Di, Dj, plus lower order terms. And since this, the principal symbol is matrix valued, maybe I should put an identity matrix here in front. But of course, if you want to talk about scalar wave equations, you just ignore this E here, and then you're talking about smooth functions, and this just means that you have the wave equation with an arbitrary smooth potential and an arbitrary smooth vector field that you can add. So that covers the case, of potentials and electromagnetic fields and whatever you want to add. Okay, so I think in matrix notation, this means that the principal symbol of P, so I'm going to use the same notation, is just equal to the metric at the point xi. Xi is a covector, so if you expand this into a polynomial, then what you get is the principal symbol is the metric. So in other words, normally hyperbolic just means the principal symbol is the metric. And there is an extremely strong solution theory for this. Doesn't get any stronger than that, I think. Let's maybe say what the definition here is. So it's something that in the physics literature is called the retarded and advanced fundamental solutions. So let's say what this is. So a continuous map G, let's call it plus minus. So this takes a test function on M, compactly supported and smooth. And it maps to a smooth function on M, not compactly supported. So we call this a retarded fundamental solution, an advanced fundamental solution. If the following is true, so first of all, it's a two-sided inverse of P on compactly supported smooth sections. Sorry, I should probably write here the sections. And at some point, I'll stop doing that, but still not there yet. So we have an inverse, a two-sided inverse, but it has the following. It maps the support of this test function to the future and to the past. So G plus minus plus minus of F is a subset of J plus minus of the support of F. They are distinguished in this way. And what's the future and the past? So J plus minus of K. That's this. I'm just going to say it because the sentence is incredibly long. So by picture, so you take this compact set K, and then J plus is everything that you get by taking a causal future-directed curve, and you emanate from K and you end up somewhere else. And all these points that you get in this way are called J plus. Okay. And all the points you get from taking past directed curves, causal curves, is called the past, J minus of K. So this is what's called a retarded advanced fundamental solution. Now, what do I mean by continuous? So here you have the usual C0 infinity topology, and you have the usual C infinity, so uniform convergence of all derivatives on compact sets. I also use the metric to identify distributions and functions, and I don't say too much about this anymore. And what's the theorem now is that they exist and are unique in our context. And this extreme generality, I would say, the theorem, this is due to Leray, I think. And also Harama. There are modern expositories that I'll talk about later. So maybe I'll mention them now. So there's a very nice book by Günther with a horrible typesetting, but it's a nice book, which is, I think, what is it called? The Huygens principle. So that's, everything is there. Then there is a nice paper by Helga Baum and Ines Katt. I think it was written for Günther's birthday. So they summarized this, and it's a short expository which explains this construction. And then if you look outside, there is an ESI book, the European Mathematical Society, by Baer, and Pfeffle, where they write this up in great detail, also for vector bundles. You can look there and look this up. What I'm going to just summarize very briefly here. So what's the assumptions of the theorem? So for some reason I changed the notation here. So it's globally hyperbolic. And of course I'm assuming here that M is a globally hyperbolic spacetime. Sorry? Yeah, it's normally hyperbolic. Thank you. So this implies that there exist unique P plus minus, which are retarded and advanced fundamental solutions. So I should say that that's the first stage. And so, you can develop a taste for what your favorite proof of this is, because the existence of such solution is just equivalent to this being able to solve the Cauchy problem. So how do you solve the Cauchy problem? If you're classically trained, maybe you take a modifier and then you use, Picard-Lindelöf or something like that for symmetric hyperbolic systems. Or if you like the Fourier transform, there are also Fourier integral operator techniques that you can find in the book of Strohmaier, I think. Also is proved. But that's not the classical way. The way Hadamard does it gives you very precise information about what these G plus minus look like. And so I'm going to continue writing now, because there is much more to be said about these. So locally, and by this I mean near the diagonal, I'm going to regret calling the diagonal delta, but yeah. So that's the diagonal x in M. G plus minus has the following form. There is a so-called an expansion which is called the Hadamard expansion, which gives very precise geometric information about these distributions. If I run out of board space now. No. So the Hadamard expansion predates Fourier integral operator constructions and gives more precise local information. You will see in a second. So let's call this neighborhood U near, so namely, let U be sufficiently small neighborhood of this diagonal in M cross M. So I'm talking about points which are really close to each other. And there was this kind of legal disclaimer that I had written here, but I think I didn't write it on the board. So the disclaimer says that I'm going to identify distributional kernels and maps. So maybe I should still write it somewhere here. So I identify, or we identify the maps from C naught infinity of M to C, well, D dash actually, of M with distributional kernels. Let's call the Schwarz kernel. And these kernels then, and I'm doing this to fix the notation. So we're acting on this vector bundle E, and then you wonder where the kernel is, and the kernel, of course, then lives on M cross M. But now the fiber maps from EX to EY, right? So we have the dual here, and then there is this box tensor product. So the fiber at X, Y is EX tensor EY star. That's this so-called outer tensor product. So anyway, so I'm going to do that. If you don't care about bundles, then you can ignore this. Okay, so that's the disclaimer here. Okay, what did I want to say? So G plus minus and plus minus restricted to U. So I'm taking this distributional kernel and I'm restricting it to U. Has the following expansion. So this has a very specific form. So it starts with j equal to 0, and it goes up to n plus n minus 2 over 2. Then there are some coefficients. I'm going to explain what all this means. So these are called the Hadamard coefficients. And then there's so-called Riesz distributions, which were, I guess, introduced by Hadamard, but Riesz found a very nice way to introduce them. So what are these Hadamard coefficients? Of course, this doesn't say anything yet because I didn't say what any of this is. But so this is in, so it's an expansion of the following type. So first of all, this becomes smoother and smoother the more terms you subtract, but it also becomes smaller and smaller near the diagonal. So it's in that sense, it's an expansion. So it's in Cn of u. And it's also of order gamma n. And of course, I will have to say what all this means, right? Gamma plus minus n. Okay, so now let's fill this with a little bit of flash here. What's gamma? Gamma is going to be, so maybe I'm saying it first before I write it down. So on a Lorentzian manifold, if you have points close enough to each other, then there exists a unique geodesic connecting them, right? And you have normal coordinates, and you can use these normal coordinates to give something which you would normally call the Lorentzian distance function, which is not really a distance, it's just, you know, the usual Minkowski inner product, so to say, written in terms of geodesic coordinates. So that's going to be our gamma. So here, what's gamma? Gamma of x comma y is just, so, well, we take the exponential map, the -1 at the point y, apply it to x, so we find this geodesic, and then we apply the map little gamma, and little gamma is just going to be x naught squared minus x1 squared minus xn minus 1 squared, right? So that's just the Lorentzian distance function squared in Riemannian coordinates. That's what this is. What's gamma plus minus of beta to the power beta? So here beta is going to be, yeah, let it be greater 0 for a moment. So then gamma plus minus to the power beta. So this is going to be gamma to the power beta of x comma y if x is in the future of y. So if, how do I write this? X is in the future of y, or in the past of y. And otherwise, it's 0. This is, for example, if beta is 0, then this is just the constant inside the forward light cone, for example, and it's 0 everywhere else. So actually, of course, the real part of beta has to be greater 0 for this to make sense. And I think Riesz's contribution was that as a distribution, you can actually meromorphically continue this. So this extends meromorphically to the entire complex plane as a family of distributions, and you can get rid of the poles. So it's sometimes called Riesz distributions in the Euclidean context, but the Lorentzian context is very similar. You can get rid of this by multiplying by certain functions, gamma functions, to get rid of the poles. So it's convenient to introduce a constant C beta n, which is 2 to the power minus n minus 2 beta pi to the 2 minus n over 2 divided by beta plus n minus 2 divided by 2 factorials, beta factorial. And I mean by factorial, I really mean gamma of either x plus 1 or x minus 1. I don't have access to Wikipedia at the moment. And then the theorem says that, well, you consider ER plus minus to the beta. Where is the index? Is it upper or lower? Oh yeah, it's the lower index. Okay, that's good. Okay, that's 2c beta comma n gamma plus minus to the power beta. So it turns out that this is a holomorphic family of distributions. Holomorphic family of distributions. Okay, where is this family? It's in D dash U cross U, in D dash U, taking values in, well, no, maybe I'm not taking values yet. So this is just the distribution in this neighborhood of the diagonal. Okay, so these are the very well-defined distributions. So maybe it's not a bad idea what it looks like for the 1 plus 1 dimensional wave equation. So I reasoned, yeah? Yes? So, oh, that's the quadratic form, yeah. Yeah, so n minus 1, right? So if you apply gamma to a vector, you get a number. On M, so you take the... okay, I see what you mean, yeah. Maybe there is a mild notational inconsistency here. Is it? No, wait a second. So yeah, it's fine, I think. G, what's G? Oh no, so you have X and Y, right? No. Little gamma. Okay, so yeah, you're right. Okay, maybe let's, you're right, so, no, you're right, of course, yeah, it should be G, minus G, right? Minus, yeah. But I can also, no, you're correct, that's a good point, actually. So using an orthonormal basis in, sorry. Yeah. So in the cotangent bundle, or the tangent bundle, maybe better to identify. No, you're right, it should have been the metric, yeah. Okay, what do I identify? Rn, I guess, with dpm. Yeah. Okay, that's a good point, actually. Thank you. So yeah, maybe it's not a bad idea to maybe look at this for a moment and see what it looks like in a picture. No. But it's still, of course, the question, what are these V's, right? I didn't tell you what that is, but yeah. Yes, Vj, yeah. Thank you. Yes? Can you point me? Yeah? Yes? Here. Yeah. Here, gamma to the power beta. Yeah, it's just the power. So these are, well, in Minkowski space, these are homogeneous distributions that have the, of order 2, which have their support in the forward light cone, and then you raise them to a certain power. You still have homogeneous distributions, and they are somehow distinguished by their support properties. This is a very beautiful theory. So in Euclidean space, if you do that with the ordinary distance function, you get one family of distributions. Here you get several. So the most distinguished one are the forward and the backwards one, but there are also others. Because of the light constructor, right? You have several connected components where you can make choices. Okay, so maybe, so this gamma plus, is it upper or lower? Is it? No, the R plus, yeah. R plus minus beta. So for beta positive, so what you normally get is, let's take plus, for example. When, let's say, n is equal to 2, then this is the constant function here in the light cone. So I think that if you put j equals 0, then this becomes R0. So the power is 0, and you get the constant function in the light cone. You also get other powers, but at some point, what you will have are poles. So for certain values of beta, there will be, the gamma function here will have poles. And that means that in the interior of the light cone, this Riesz distribution actually vanishes, and then it will be a singular distribution with support on the boundary of the light cone. And that's related, of course, to the Huygens principle. But yeah, we'll come back to this later. So the support properties look like this, okay? That's the support. Let's maybe erase this here. So R plus minus. The support will always be here. Sometimes the support is on the light cone, sometimes not. But most of the time, for generic values of beta, the support will be, exactly the light cone. And now remember, what are the VKs or VJs? So these are smooth functions on M, on U. These are functions of two variables, so to say. Yeah? Remember that U is a subset of M cross M. And they're determined by the following. So V0 of x comma x is the identity map on EX. Yeah, okay, maybe I should have said, realize now that it's time to introduce my bundle. So these are smooth endomorphism valued functions. So I have the box tensor product here, E star. And of course, that's restricted to E, to U. Okay, so these are smooth matrix valued functions, and they satisfy the following equation. So the first one, the V0 term, that must be equal to the identity when x is equal to y, so on the diagonal. And then they satisfy a system of transport equations that I just write down for your information. But the whole point is you can solve them. So you take the gradient of gamma. So gamma has two variables. You should take the gradient in the first variable. So that's why I write this little one here. And then you apply it to the kth Hadamard coefficient. They're called Hadamard coefficients. Minus, and then you take 1/2 in the bracket. You take the Laplace operator on functions now, so I'll write here 0, it's the Laplace operator. In the first argument, applied to gamma, minus n plus 2k, bk, and that's equal to 2k times p. So that's the box operator that's equal to, that's the p. That's not the Laplace operator on functions. In the first argument applied to the k minus first Hadamard coefficient. And this system of transport equations uniquely determine these functions. So that's a theorem. You have to prove it, of course, but I'm not going to do that. So they uniquely determine these coefficients. And once you have these coefficients, you can verify that you get something that solves the equation almost. So the way you arrive at the system here is you apply P, or box, to G plus minus, right? And so you use the product formula to expand this. There are formulas for the Riesz distributions. Well, you expect that they're expressed in terms of geodesic coordinates, and they are homogeneous, right? So they will simplify quite a bit. And you do the computation, and you get exactly this transport equation. Means that this, in the formal sense, solves the wave equation formally. Yes. Where? No, V0 is 0. Sorry, V minus 1. Yeah, that's right. You can add that, yeah, that's right. Yeah. So the way Hadamard proceeds to show this theorem is, and that's actually a theme in all the other approaches as well, except for the mollifier one, is that you find a parametric, so something that approximates the solution modulo a small error, and then you use once you have an approximate inverse, you use the Neumann series to invert it exactly. That's how this goes. And so there is a lot of, you have to write a lot because it has to be done in the right function spaces. So you do it in CK and then do it for every K and so on. But you can see how this works here. You just try to solve this here on the formal level. If you have seen, the heat equation be solved on a Riemannian manifold, if you like index theory, for example, then this is also exactly the same proof. It's really the same proof. In fact, it's even so much the same that if the manifold is a product, so if it happens so that M is equal to R cross sigma, and the metric has the form minus dt squared plus h, where h does not depend on time, so we call this an ultrastatic spacetime, these Hadamard coefficients on M are actually independent of t, and they are exactly the heat kernel coefficients, modulo some factor that I don't want to talk about because I forget it. Good. I think I still have to explain one thing, namely what is this here? That's some connection on this bundle. So I still have to explain what this is. So here, this connection here is automatically given to you once you have the operator. It's determined by the following theorem by, yeah, I forget, maybe Bochner, maybe not Bochner. Not Bochner, what's the other one? Sorry? No, also not Rhodes, okay. Weizenberg. So by the following formula, which is, I don't know if it's due to Weizenberg, but it's sometimes called the Weizenberg formula. So every normally hyperbolic operator can be uniquely written in the following form. So you take 2 times the covariant derivative, first on the vector bundle, and then again in the vector bundle tensor T star M, where you use the Levi-Civita connection coming from G, right? So there is nothing arbitrary here. So that gives you a normally hyperbolic operator. And so for every P, there is a unique such connection plus a potential. So W here is a smooth function. So the connection is given to you by the operator. You don't have to actually postulate it. So this is a smooth function on M, taking values in the endomorphisms of E. So we call it a matrix valued potential. It's completely determined by P, and so is the connection. And that's the connection that you have to use here. Good. So did I miss anything? I hope not. So this gives you precisely a singularity expansion of these retarded and advanced fundamental solutions on the diagonal. And so does Fourier integral operator calculus, for example, if you know what this means. And I'll talk about Fourier integral operators tomorrow. But it's much more precise because it gives you all the terms, not just the first one. It's very precise. Okay, a couple of examples. Yeah, so here you are a function of one variable. So this field would look like this, right? So W of X will be an endomorphism of the bundle E of X, right? Whereas if you take an element like the Hadamard coefficient, for example, V0 of X comma Y, this will be a map from E of Y to E of X. That's the difference. Yeah. So in other words, it's an element in, I'm getting this right, I hope, EX tensor EY star. Yeah. So maybe I should give you a little teaser. All this is completely covariant. So I have not introduced any artificial coordinates. If you want to do that on a Kerr space-time, you can do it. There is no, I don't need a Cauchy surface or anything. And the whole point of this business is when you have a killing field, you can do spectral theory without reference to a Cauchy surface. You can get quite far with this. So that's, we'll come to this the next lecture, not today. And everything is encoded in this retarded and advanced fundamental solutions. And we'll see how to do that. Okay, so examples. For example, number 1, it's really just for you to relax for a second, because you already know that the examples is the D'Alembert operator on functions, namely minus trace squared. I don't think I need a trace actually here. I know I do need a trace. Or in other words, that's delta D if you like differential and co-differentials. Is that right? Yeah, it's the sign is correct. Thanks to the incorrectly chosen sign convention. So and I'm considering this as an operator on C. Okay, so that's the function case. If you want, you can add a mass term to make it the Klein-Gordon equation. You can also minimally couple it by adding, squares or the scalar curvature or any other function of the scalar curvature, whatever you want to do. So maybe that's already example number 2. You can also do the Klein-Gordon equation by taking Laplace metric wave operator. This would be box G here for some m, or m greater equal 0. In fact, you can even choose m in imaginary and make it negative. That solution theory will still work just fine. The third one is the spin Dirac operator. So here E is the spinor bundle. Here I'm assuming that I'm giving a spin structure. M is spin. But of course, M is spin if and only if sigma is spin. In the physical dimension, by the way, that's very often the case. So orientability of a three-manifold is enough to guarantee its parallelizability, actually. So you will have a spin structure always in the physics. If you think that the dimension is 4, which I do, then there is a spin structure. And let's say D is then the Dirac operator associated with the spin structure. And what this means is the Dirac operator has the structure that if you square it, then you get a normally hyperbolic operator. And the spinor bundle one has even more structure. It's somehow canonically constructed out of this metric and this topological thing, which is the spin structure. But what you really need from this here is so that it satisfies the following formula, and I'll explain in a second why I'm mentioning this formula. So D squared, if you square it, it's an extremely important formula. You get minus trace Laplace squared. So that's the connection from the spinor bundle, the spin connection, which is also the connection that you get from the square of the Dirac operator. Yeah? So that's the first part of the theorem. And the second part of the theorem, that the potential is just a quarter of the scalar curvature. The Lorentzian scalar curvature, right? Not the Riemannian one. So in the product case, when you have this product structure as before, that's the same as the scalar curvature on sigma, but in general, of course, it is not. So this is called so now I can write down all these names. So Schrödinger, of course, because we're in the Schrödinger Institute and we see pictures of Schrödinger everywhere, but we should also see a formula of Schrödinger. So this is Schrödinger's formula. But it's not called Schrödinger's formula normally. It's called the Lichner-Horowitz formula. But it turns out that there were a lot of people related to this. So maybe let's add a couple of more names. So Weizenberg also. But if you read the paper of Schrödinger, the formula is there, even for the spin C case. Sorry? Where? No, Weizenberg, not Bach. No Bach. Yeah. Which one? That's the scalar curvature. Yeah, I see. It's not skull, it's skull. No mistakes there. So that's the scalar curvature. But the Lorentzian one, right? So Lorentzian scalar curvature. So this is a very important formula in the business of positive scalar curvature on Riemannian manifolds. Okay, so but you say, well, that's not a normally hyperbolic operator, but this one is. And what you can see from this immediately is that the Dirac operator also has retarded and advanced fundamental solutions. So D also has retarded and advanced fundamental solutions. Namely, you take the one for D squared and you just apply for D squared and you just apply D to it, right? So let's call them maybe I have another letter for this F plus minus. It's just you take D and you apply it to G plus minus, where G plus, I think I had a lower index. The covariant functor. So this here is the retarded and advanced fundamental solution for D squared. Yeah, so you automatically get them for the Dirac equation. So in this way, so you can see that even if you say, well, I'm only interested in the Dirac equation, some people do, you can still square it and you can use the Hadamard construction. So that's very nice, I think. Good. There are some symmetries that this problem has. So I claimed earlier that this is the same as solving the Cauchy problem. So maybe I'm putting myself at risk here and do an integration by parts on the board. This is going to be important later. So there is something which is called, which actually comes, and I learned this from quantum field theory and curved spacetimes, but it's incredibly useful to just do PDEs on spacetimes. And this is called the Pauli-Jordan commutator distributions. It certainly has a fancy name. Okay, so first let me say that, so if you take the adjoint of a normally hyperbolic operator, and by this I mean the formal adjoint, as a differential operator, it has a formal adjoint, and then this formal adjoint will act on the dual bundle, right? But it's also a normally hyperbolic operator, so it also has retarded and advanced fundamental solutions, and if you take those, it turns out that the retarded and the advanced ones reverse, because if you take the adjoint, the arguments switch, so future becomes past. So the adjoint, that's the formal adjoint, is actually the same as G plus minus, where G plus minus star is the retarded fundamental and the advanced fundamental solution of the adjoint operator. And what you can see from this is that the Klein-Gordon equation is actually self-adjoint, formally self-adjoint. And you don't get any Hilbert space out of this, or not in a good way. But what you can see is that this translates to symmetry properties of G plus and G minus. But what this is useful for is abstract nonsense. Fantastic, I love this. So the G plus minus therefore automatically immediately extend to maps between distribution spaces, right? Well, because that's the dual of C naught infinity, and that's the dual of C infinity. So automatically get that for free, just because of the symmetry property. So without the dream of every pure mathematician, you don't work and you just get it. Okay, so that allows us to solve the Cauchy problem. So by continuity, by duality, this is a continuous extension. Okay, solution of the Cauchy problem. Maybe I can get rid of this integration by parts business by using this trick that I do it in the break, so to say. So what's the Cauchy problem? I want to solve P f equals 0, and I give myself initial data. So this time I fix a Cauchy surface, sigma the Cauchy surface. For the Cauchy problem, you see I need a Cauchy surface to state it, but the G's, they are independent of the Cauchy, of any Cauchy surface. So what I want is that I give myself initial data on sigma. So this is the future pointing normal derivative here. The future pointing normal vector field I call nu. And I take this restriction here, and I want this to be G0. I was criticized by using G, but G0, that's not the metric. So G1, so these are the initial data. And so it turns out that the solution has a unique solution. And in fact, you can give this solution explicitly in terms of G plus and G minus. And the way you do it is you take F. So you first of all are clever enough to introduce this Pauli-Jordan commutator distribution, which is G plus minus G minus. So now note that G plus minus G minus is no longer an inverse, but it actually solves the equation. Right? If you apply P to it, it will just map to the space of solutions. So this whatever you apply G to, it will solve the wave equation. So okay, let's apply it to some distribution. Namely, we just apply it to the following distribution. We take G0, so that's a function on the Cauchy surface, and I take the normal derivative of the delta function, and I think of that as a distribution in space-time. So I hope that it will be understood what this means here. Oh, I think I made a mistake. Oh, let me do it like this. delta dash, that's why I have it in the notes, maybe I'll stick to this, F0, G0, plus a delta distribution that is formed from G1. And I should say what this means. Maybe here. I'm continuing. Yeah. So what I mean by this is, if I take this delta distribution, G0, and I want delta dash, and I have to declare what it does with a test function phi. So what I do is I take minus, and then I take the normal derivative of that test function, and I multiply it by G0. And then I integrate that over the Cauchy surface. So you can see that this is really just the unit normal derivative of the delta distribution sitting on the Cauchy surface. And in the same way, it looks like I have to do this computation. So G1. So they switch roles here. This is just the delta distribution on sigma that I smear out with G1. So this is G1 of x, phi of x, dx, and I integrate this over the Cauchy surface. So you have these distributions, you apply this operator G to it, and you get the smooth solution of the Cauchy problem. So they are, of course, because f and g are, I didn't say what function spaces they're in, let's say they are compactly supported, smooth functions, so these will be in E dash, so because of this duality argument, I get a distributional solution, but then the statement is this distributional solution is actually a smooth solution, and it solves this Cauchy problem. Okay, maybe I'll do that now. I was afraid of it, and so I practiced it in the morning. So let's prove that here, because I think every lecture I didn't prove anything, right? Just said a lot of things, but didn't prove actually anything. So now I feel bad. So that's an integration by parts argument. So let's prove that. So there is a bit more to say here that I won't prove. Namely, it will turn out tomorrow that G is a Fourier integral operator, and it follows from this that F is smooth. I'm not telling you how this is done. Well, I guess you could get it out of the Hadamard expansion, actually, but we don't do that. Okay, but I just want to show you why this formula is true, why it's exactly that here. So that F plus, so this is G plus, applied to this distribution here. Let's give this a name. So yeah, name. Distribution D is really bad name for a distribution. U, okay, let's call it U. U, the distribution U. So this is this one here. And so I apply G plus to U, but that's just the same as G applied to U. And then I restrict it to the future of sigma plus, right? Of sigma. So in the same way, G minus is just so minus G restricted to the past. And now I want to see what happens if I apply a test function to something that I forgot. Uh-oh. Okay, so I checked that they can actually edit the video and cut something out afterwards. It's always good to make sure that this is the case. So I want to apply a test function. Yeah, maybe the test function I want to apply something to is, well, let's choose a test function phi in C naught infinity of M. And then I think it's box phi that I integrate with F plus. Hope that's right. I completely forgot because I'm standing at the board. Okay, let me just think for a moment. Okay, I think it's okay, but let's see. So let's say M plus is the future this Cauchy surface. And I'm only integrating over m plus here. So this solves the wave equation on m plus because I apply the distribution to g plus. But the support of this distribution is, on the Cauchy surface. So to the future of the Cauchy surface, the right-hand side of the wave equation is to 0. So this solves the wave equation. And I can use this Green's formula. So this is the same as, if I apply Green's formula, then this solves the wave equation, so this goes away. And then what I get is modulo a sign that I don't remember. So the normal derivative of phi times u plus. And then I get the normal derivative of u plus times phi. This is Green's identity. And so this should be the same as, I think it works, okay. So, sorry? No, there is no u. It's because I usually use u for that letter. So f plus, right? F plus and f plus here. That's the right thing. So these are the Cauchy data of the solution f. So this is actually the same as the distribution that I'm claiming. So this is the distribution delta. There is a minus here, right? So maybe it's minus here and plus here and minus here. So yeah, you can see how this works out if one concentrates really hard. So there is no minus here. It's minus plus. I think I did it twice now. So what I'm getting here is the Cauchy data as I claimed. So delta dash with f on sigma plus delta sigma and then the normal derivative of f. And then that's the test function phi. At the same time, this is the distributional derivative of f plus. But the distributional derivative of f plus is u. So this must be the same as u phi. And now you can compare, and you can see that the solution has the same Cauchy data. Okay. So that shows that this is really a solution. And this also allows you to formulate the Cauchy problem without too much reference to the Cauchy surface, and we will see in the next 3 lectures how this can be used to talk about spectral theory without actually specifying the Cauchy surface. So I think I'll stop here.